This is a Geek Leader podcast, and I'm your host, John Rauda. This show is all about helping us grow as leaders, become better technologists, and improve our lives both at work and at home. I hope you enjoy the show and learn a lot. Hello, world, and welcome to a Geek Leader podcast. I'm your host, John Rauda. Today's sponsor is A2 Hosting. I've been using A2 Hosting solid-state hosting solutions for our website at geekleader.com for many years now, and absolutely love their support, their service, and all the features that you get. You get access to cPanel. You get all of the things that you can imagine for a great WordPress experience, including their A2 optimized WordPress, which does extra security checks, extra lockdown. You can lock down your editor file so you can't edit anything inside there. You get alerts whenever there are file changes that are done. You can also do automatic updates, backups, and more with A2 Hosting. So highly recommend it. Go to geekleader.com/A2 to get more information and to sign up for their solid state turbocharged speed hosting today. Again, that's at geekleader.com/A2. All right, Geek Leaders. Today, I'm honored to have Rishabh Poddar on the show. He is the CEO and co-founder of Opaque Systems, and we're going to talk about cryptography. We're going to talk about security. We're going to talk about secure enclaves and encryption, and some pretty cool stuff today. Rishabh, welcome to the show.
Thank you so much for having me, John. It's a pleasure. And yeah, excited to tell you more about Opaque and what we're up to here.
Yeah, awesome. If you don't mind, just tell the audience a little bit about your background and how you got to where you are today, and what is it that you guys do over at Opaque?
Absolutely. So I'm Rishabh. I'm the CEO and co-founder of Opaque Systems. We're a company that was born out of research and open source at UC Berkeley. So my background is in system security. I did my PhD at UC Berkeley and developed open source as a part of the research that we were doing at Berkeley. And we saw a lot of excitement and urgency around what we were building. And really, that is how we decided to take the plunge in 2021. And we started Opaque to productize and commercialize the technology that we were building. Just a quick background on how we came to be. So the research, I was part of this lab at Berkeley called the RISE Lab. And our lab we worked closely with partners and industry as well as government. The research was very well funded by government grants, but also big tech companies like Google, Amazon, Facebook, Microsoft, and including the more traditional Fortune 500 type companies, banks like Scotiabank, JP Morgan, Capital One, companies like IBM, Ericsson, NVIDIA, who funded the lab to gain access to our research so that they could adopt it and deploy it in practice. And the problems we solved were always informed in close partnership with these entities as well. So because we were always motivated by solving problems that would be super important, let's say 5 years down the line, at the time when we started doing the research. And this has been the ethos of the lab for a while. We've had a very entrepreneurial culture. The lab's given rise to many successful startups born out of research. Databricks is a very good example. That's a good role model for us to follow. But in addition to Databricks, there have been many that have followed since as well as a result of this close partnership model that we have with industry. And in our case, in the case of our open source and research, companies like Ant Financial and IBM contributed code back to our research and open source before deploying it in practice for their own use cases. We already began doing POCs with other larger companies as well. And soon they really began asking us for capabilities and features that go outside the purview of a typical research lab, essentially nudging us towards starting the company. And that is how Opaque was born. And that is how we decided to take the plunge. And me with my research colleagues and our PhD advisors, frankly. So my PhD advisor, Raluca Popa, she's an expert, a world-renowned expert in cryptography and system security. She's the president of the company. Jon Stoica, who was the founder of Databricks and the first CEO of Databricks for a number of years, he's also a co-founder. And along with Raluca and Jon, Wenting and Chester were grad student colleagues with me, and we worked on the research and open source together, and we started the company together as well. So that's essentially a quick story around how Opaque came to be.
And what exactly do you guys offer that, when it comes to encryption that's, of interest to us engineers and software developers and companies that are working with data?
Yeah, absolutely. So if we take a step back and look
Hmm.
at the state of data protection that exists in the world today, right? As an industry, we know how to encrypt data at rest. So when it's
Hmm.
stored on disk or on the cloud, we can encrypt it using standard mechanisms. Uh, from a technology perspective, it's a solved problem. Um, we also know how to encrypt data in transit. When data is being sent over the network from a source to destination, we can once again encrypt it using standard encryption protocols like TLS and HTTPS and so forth. What we don't have widely deployed solutions for today, and this is also the key place where data is at risk and data becomes vulnerable, is encryption in use. Right now, when data needs to be processed, it needs to be unencrypted in memory or in the machine where it's being operated on using software or so forth. And it needs to be exposed in the clear. And this makes it vulnerable to other software that exists on the machine, to entities like the software provider, the cloud platform where the processing might be happening, or system administrators, or anyone who has access to the machine also has access to that data. So encryption in use is something that has not been possible for the longest time. And essentially, what we enable is we provide a platform that allows you to get insights and run analytics and train models on confidential data while keeping it protected and encrypted even during processing. So data remains protected even when it's in use. So effectively, now the data remains protected throughout its life cycle in all three states in which it can exist: at rest, in transit, and now also in use. And one very exciting part of this capability is that now you can, one, activate and get insights from confidential data instead of having to lock it down on-prem or in silos.
Hmm.
And you can also collaborate on confidential data. Uh, Data owners can share confidential data with other entities within their business ecosystem. So these could be teams within the same organization, different departments, different jurisdictions, different geographical locations, or these could be different organizations entirely. They can now each individually encrypt their data, pool it together in the cloud, and then use Opaque to jointly run analytics or jointly train models on the collective combined encrypted data without having to show the confidential data to anyone. No one gets to see it. Not the other data teams can't see it. Opaque can't see it. The cloud platform can't see it either. It remains protected and encrypted even when it's in use. And this is really a very powerful paradigm that we see occur across industries and that we see urgency and excitement around across industries. So that, in a nutshell, is what Opaque is about, and what the open source that we built, the MC2 project, which is available under a permissive license on GitHub. This is really the problem that we are solving.
Yeah, wow. When I always think back to like the early days of my software engineering journey, it was we learned about encryption as being something that's locked away. And once you've locked
Yes,
it, unless you have that key, you can't actually use it. It's like in a safe somewhere. And now we're talking about basically putting your hands through that safe and using that data without actually unlocking it.
that's an excellent analogy. Absolutely. So you can't take the data out of the safe, but you can
Right.
still put your hands inside and do things with it,
Yeah, and
and
I
get
think of
insight.
those. What are those like the NICUs where the babies, it locked away somewhere to keep it safe from outside bacteria, but they have those spaces where the doctors can put their hands through and be able to manipulate. Uh,
That's a wonderful analogy, John. I think I'm going to use it in the future.
yeah, feel free to have that one. But that seems super intriguing to me. How did you guys get the idea of wanting to be able to use data while it's encrypted and encryption in use? I've never even heard that term, encryption in use.
Yes. So cryptographers have tried to solve this problem for a long time now. And in around 2010 and after that, techniques that they developed techniques that could allow you to keep data encrypted using specialized cryptographic protocols while at once running computation or processing it. So in the theory or in the research domain, this problem has existed and has been known for a while. But it's now we are starting to see traction and movement around it in industry as well. So in the last decade, as the cryptographic protocols like homomorphic encryption or secure multi-party computation became practical, there was sort of an education that happened in industry, in the more regulated sectors perhaps, around the promise of this new technology. Just the ability to be able to compute on encrypted data.
Right.
At Opaque, our approach is not based on those purely cryptographic protocols, and I'll tell you why. But essentially, the reason is that purely cryptographic protocols like homomorphic encryption or secure multi-party computation, well, beautiful technologies. Half my PhD thesis was on that topic as well. But the problem with those approaches is that they're super resource intensive and quite slow. Things that should take seconds or minutes can take hours or days. So they're orders of magnitude slower as a result. They require orders of magnitude more resources, which makes them unsuitable for big data analytics and complex workloads like machine learning. Instead, the approach that we take at Opaque, and we took an MC2 as well, is to use confidential computing as a technology. So confidential computing is a technology that became available in the last decade, pioneered by Intel, but only became commercially available on the clouds in 2020 and so forth. And what this technology allows you to do is essentially, it allows you to create a secure black box, so to speak, or a secure trusted execution environment or an enclave within the CPU hardware itself. Whenever data is in main memory, it always remains encrypted using standard encryption when it's undergoing processing. Only when the data is loaded inside this black box, deep down within the CPU die, only there is it decrypted and processed. So you at once get this very strong security guarantee of having data encrypted and protected in use. But at the same time, you get the raw computation power of the CPU as well, without having to work or layer your processing through resource-intensive cryptographic protocols. And this technology is essentially what Opaque is based on. We provide the software ecosystem for analytics and AI that powers this specialized hardware capability. Intel actually gave us access to their secure enclave machines even before they were commercially available, by the way, to foster research in the lab. And they worked with a number of other research labs as well. And this technology became available on Azure in 2020. So the barrier to adopting this specialized hardware has now gone away, because now you can just rent a regular, any other virtual machine on the cloud that has this capability with it. So that runs on physical machines that has this capability. So you don't have to procure specialized hardware yourself to take advantage of this encryption and use, or data protection and use capability. You can just work with regular cloud providers. And we provide the software ecosystem that powers it and makes it secure from an end-to-end perspective and highly easy to use and scalable for big data analytics and machine learning.
So I don't have to buy any special hardware. I can just go to my Azure instance and spin up a VM that, has all this hardware in the cloud, and then run your software on there. And then all of my data that I'm processing for my data lake or whatever could then be protected?
So yes to the first part, but there are nuances
Okay.
to the second. In the sense that, yes, now you can just log into your Azure account and spin up the correct VMs, the correct VM SKUs that will then run on physical servers that have this capability. So so yes, that is something that you can already do. Now, in terms of just by virtue of running this particular VM, do you get data protection? And the answer is not quite.
Not quite.
No. And the reason for that is twofold. One is it depends on the type of hardware technology that the VM is backed by. So, for example, Intel has their version of this technology. It's called Intel SGX. Now, to take advantage of Intel SGX, you need to have bespoke software that can speak the language of SGX, or that is programmed against the enclave's APIs. An analogy here is you have GPUs for accelerating machine learning workloads. But just because you have GPU hardware in your cloud cluster, your data processing won't automatically get sped up. You need to use frameworks that can speak the language of the GPUs. So you need to have support for CUDA and so forth within the software frameworks that need to be run, that you want to run against GPUs. Similarly, with Intel's enclaves, the software that you want to run needs to be architected against this capability as well. This is one part of the larger problem that you need to solve. You now also need to think about getting data securely in and out of the enclave and the machine as well. Your data can be stored somewhere on the cloud or on-prem. How do you make sure that the data is transferred securely? Because the data is decrypted inside the enclave, you need to be able to transfer your keys securely to the enclave as well over secure protocols. You need to be able to verify that the software that's running inside the enclave is actually software that you have audited and trust to not have vulnerabilities. So there is this whole process, this cryptographic process called remote attestation, that allows you to bootstrap that trust. That, okay, now you are in fact speaking to enclave-enabled machines. The machines that have not been swapped out, or incorrect machines have not been spun up, for example. So you need to bootstrap that trust as well. And when you're collaborating with other entities, you should not be allowed to run whatever you want on the data, right? So if you and I are collaborating on some workload and we are sharing data, you should not be allowed to do whatever you want with my data. You should only be allowed to do what I permit you to do with my data. For example, you shouldn't be allowed to run a script that says, give me access to all of Rishabh's data, because that will trivially violate the confidentiality protection that you sought. So you also need advanced software-based governance mechanisms that can provably protect the data processing that's happening within the enclaves. So there are all of these issues that one needs to be aware of as well, and that software frameworks that are built to protect data inside enclaves that they need to take these factors into account as well. So which is why it's not quite as easy as just simply taking your workload and moving it to a confidential computing environment in the cloud. Because from the perspective of end-to-end security, all these other issues and factors come up. Now, on the other hand, Intel SGX is one example of a confidential computing technology. You also have confidential VMs, like AMD's confidential VMs, that convert the entire virtual machine into a trusted execution environment. The difference is that in the Intel enclave case, you only needed to trust that tiny piece of code that's running inside the enclave to not be malicious or not to be misbehaving with your data. You did not need to trust any other software in the machine. You don't even need to trust the operating system or the hypervisor or any other privileged software. Not even attackers who break in and gain root access will be able to take a look at the data. With confidential VMs, all of this other software is within your trust domain. So you need to have trust that, okay, the operating system will not exfiltrate my data. But what you get as a benefit is you don't need to program a software specially against the API of the hardware. You can run legacy software as well. So confidential VMs afford more flexibility, but the other issues still stay in place. Around attestation and around working with data encrypted with multiple keys, and around enforcing policies so that the data analyst is not allowed to do whatever they want with the data. They can only execute some
like certain commands on
that
it or
you
whatever.
permit them to do. All of these holistic all of these problems need to be solved in any end-to-end framework. And we essentially, our mission is to make that frictionless from the perspective of the user. To use confidential computing, you should not have to be an expert in confidential computing or a security expert, or or have to worry about, okay, how do I solve all these other problems? It should be as easy for you to run analytics or train models on confidential data as it is right now for you to work with regular vanilla data.
Mm-hmm.
And we take care of everything else.
Yeah.
So that's really where we come into the confidential computing world.
Yeah, you make it sound like when I'm thinking about like the difference between how a developer would use this, you're saying that basically instead of having to learn all of that encryption algorithms and all the things you have to think about and be prepared for, your software will kind of handle this for them.
Yes. So they essentially using Opaque is roughly a 3-step process.
Okay.
The first thing you need to do is you can use the Opaque client to encrypt your data using your own key, using standard encryption mechanisms, and upload it to a location of your choice. You can upload it to Azure Blob Storage, for example, or directly to the machines where you want to run Opaque.
Mm-hmm.
Then you can use the client through a browser-based interface to orchestrate or manage the cloud cluster, run Opaque, submit jobs using a notebook-like interface that then get executed within enclaves over the encrypted confidential data. And the key thing here is you can submit the same jobs as you would with a regular framework for big data analytics without having to learn a different language, for example.
So I don't have to recode it all, is what you're saying. I can just use it the way. Okay.
Exactly. So for example, we have support for Apache Spark SQL. You can submit the same Spark SQL queries or the same Spark SQL jobs, for example, in Scala or Python or SQL. Mm-hmm. And that will now get executed over your confidential data. So you don't have to learn any new languages or APIs. All of the security enforcement sort of gets abstracted away from the data scientist. And once the job is done, you download the data back to your client, and where it gets decrypted, and you can see the results and take action based on the output. So awesome. All of the complexities get abstracted away as a result.
So when I'm thinking about this, is that there's so many times where I've heard, well, oh, the data's been anonymized, and then somehow somebody finds a way to back engineer it. And it turns out like, if you use something like this with a protected enclave that's completely, secured, you get the results without ever actually getting the data. So it can't be de-anonymized. Is that what we're kind of getting at? Potentially?
So two parts to it. There is a nuance. I mean, you're right, but there is a nuance here. You can only learn the information that you can learn about the data is based on what results you're allowed to get from the data. So if I permit you to run certain queries, for example, then the only thing you will learn is whatever the results of that query reveal to you. But I have, if I am fine with you running that query, then that's good. You can't learn anything by looking at the data itself. So the problem with traditional anonymization techniques, etc., is that they're known to be insecure, especially if you have access to other unencrypted fields. Then you can researchers have shown how you can use this auxiliary data to reverse engineer the anonymized fields, so to speak. Also, if you want to run computation on the anonymized fields, for example, if I have a list of names and I have anonymized them, and you have a list of names that you have anonymized, and I want to intersect these two fields to identify which names we have in common, with traditional anonymization, the way that would happen is all of those names would get mapped to a deterministic token, so to speak. And because they're deterministic, we can now check equality or perform other operations on it. But this is problematic because deterministic tokenization can be broken. You also get to, if our names map to the same tokens, then you know which names I have in my data set simply by virtue of they map to the same value. So what you really, so encryption addresses this problem, or standard randomized encryption addresses this problem, because now all your names will get mapped to random ciphertexts. And all my names will also get mapped to random ciphertexts. So if we were to look at the encrypted data on their own, we would learn no information at all. And we can, instead of just encrypting names, we can encrypt the entire data set as well. I can encrypt my entire data set. You can encrypt your entire data set. The magic is that even though we have now encrypted our entire data sets to random gibberish, you can still combine them under the hood. You can still run computations on them under the hood. So at once you get much stronger security guarantees than traditional mechanisms for protecting data like anonymization or pseudonymization or masking. But you also get higher utility as well, because now you can share more data without having to worry about it leaking information about the underlying data set, and get more insights and get better insights as a result. So you really get the best of both worlds: strong security as well as higher utility.
Oh, wow. Yeah, that's awesome. This is so fascinating. So where do you see this going, like in the next 3 to 5 years?
That's an excellent question. And honestly, I'm seeing the confidential computing is or privacy enhancing technologies like confidential computing. They're a young emerging category. So as an industry, I think we need to do more around educating practitioners and users around the possibilities of what this technology can enable. So Gartner, for example, predicts that 75% of the world's data will need to be protected and processed using technologies like this in the next few years. So we're going to see more and more adoption as awareness around privacy enhancing technologies like confidential computing grows. Because it's not like we're telling organizations that, you have some problem X that you have been solving using solution A, come use opaque or adopt confidential computing because we can do it better. No, we're literally telling them the things that you have not been able to do so far become possible as a result. So for example, banks can now collaborate to identify financial criminals. In the absence of a technology like opaques, the best that each bank can do is look at its individual transaction data, mine that for patterns, and then flag suspicious transactions. But this is a lengthy, cumbersome process that has very high false positives. It's not particularly robust because you only have a partial view of the data. But if banks and financial institutions could collaborate, they could pool all the data sets together and then jointly analyze the data set to identify patterns, train better models, more robust models, and identify human traffickers or money launderers. They can't do this data sharing right now because the data is super confidential. And they either have to trust other entities or trust a third party to be a good custodian of its data. Or in many cases, there are privacy laws and regulations that prevent such sharing from happening in the first place. These problems go.
I can see definitely use cases of this for like medical practices too, for like, people collaborated to get the COVID vaccine, but imagine being able to collaborate even more with all your trials and the results of that without having to worry about patient confidentiality or even, stealing of, patents or things like that. All that could be kind of protected.
Yes, you actually want multiple use cases in that, actually. And I mean, COVID is a very, very good example, as you suggested. I mean, so one thing we learned during COVID, right, is that contact tracing could have helped solve the problem to a large extent. But the moment we tried to deploy contact tracing, we realized that we needed to be able to combine patient data that was held in various health repositories and silos. And the moment we tried to do that, all these patient confidentiality concerns, like you outlined, came to the forefront, thwarting those efforts to a large extent. Now, not to get ahead of myself, but had opaque been around, then maybe we could have made a dent into the problem. You can train better disease prediction models as well as a result. Monetizing IP, like you said, also becomes possible because now, let's say I have a model that I have trained that is robust and performs well. How can I let you take advantage of this? How can I share this model with you without you getting access to the model itself? The answer is, again, in confidential computing, because you can run the model inside a confidential computing environment and run inference against it securely. So I don't get to see your data, you don't get to see my model, but we both benefit from this collaboration. So data collaboration becomes possible on confidential data as a result. And to me, that is a superbly exciting prospect.
Yeah, definitely. I think that's a huge advance forward just in society in general, something that we can benefit from when this becomes more mainstream.
Yes. So really, we can now shift from institutional trust to programmatic trust as a result. Right now, when I want anyone to work with confidential data, I need to rely on a piece of paper, so to speak, or a contract to facilitate or enable that trust.
Right.
But we can do better. We can, instead of having to trust institutions, we can now enable that trust from the technology itself. So you don't have to trust anyone. You accept the hardware itself as far as confidential computing is concerned. And you get that assurance and that strong degree of protection enabled from the technology itself. So you don't have to trust Opaque, you don't have to trust the cloud, you don't have to trust your collaborators, but you can still keep everything protected in a provable sort of way.
Yeah, I think that's awesome. I think it's definitely a new way of thinking about encryption and protection of data, and also a way of collaboration. Collaboration is kind of like I think the thing that really takes us to the next level, which is pretty awesome.
Yes.
So how can people connect with you online and learn more about the things that you guys are doing over at Opaque Systems?
Multiple avenues. My email address. Absolutely, I'm more than happy. I would love to hear from people who are interested in this technology, looking to bring this into their own organizations. My email addresses, my first name are Rishabh, that's Rishabh at opaque.co, opaque.co. We also have a website, so you can reach out to us through the website, email us at hello@opaque.co, or request a demo through the website. If you want to engage on the open source front, then we have Slack channels for community. Reach out to us through GitHub repositories, multiple ways in which people can get in touch with us. And I would love to hear from you if you are interested in Opaque or confidential computing.
Yeah, absolutely. And I'm going to link all that up in the show notes too at geekleader.com, so people can link to it there. And this has been a great conversation. I really appreciate you educating me on some of the things that are happening now with data protection and encryption and use and things like that. It's been super fascinating.
Absolutely. Thanks for having me, John. It's been a pleasure, and always happy to talk more around confidential computing and privacy preserving technologies more broadly.
Awesome. If you enjoyed that episode, please leave a rating and review in Apple Podcasts. I'd greatly appreciate that. And also, don't forget to check out merch. We have some t-shirts that I've designed that are on at geekleader.com. You can click on the merchandise section there and check that out. And also, don't forget about the books from our guests. So if you like this guest and other guests that have written books, please go ahead and check that out at geekleader.com. I would greatly appreciate it, and I'm sure they would too.